absolute values are our way of talking about the distance of a number from 0 on the number line. So more precisely, when we take a number and we write the absolute value of a, standard notation, if I'm going to write this precisely, this can be written in piecewise notation because it depends if a is positive or negative, and it's equal to a if a is greater than or equal to 0, and it's equal to minus a if a is strictly less than 0. So what is this? This is the distance. It's the distance between 0 and a. Okay, so it's how far away from 0 you are on the number line. Now, it's pretty important to be able to manipulate absolute values using very basic algebra. And all I really want to focus on are three really important things, namely addition, subtraction, multiplication, division, and taking roots. That's all I want to look at here. So here are the key algebraic properties of the absolute value. So key algebraic properties. So the first thing is the absolute value behaves very nicely when it comes to multiplication. So a multiplied by b is equal to, the absolute value of a multiplied by b is the absolute value of a multiplied by the absolute value of b. This is kind of called the multiplicative property of the absolute value. Similarly, if I take the absolute value of a quotient, it's exactly what you'd hope. It's the ratio of the individual absolute values. And the second one is obviously a caveat because you can't divide through by 0. So when I'm writing this by assumption, we're assuming b is not equal to 0 because then the absolute value would be 0. Okay, so let's look at a few examples, shall we? A few examples. So let's do kind of an interesting one, a little bit of tricky algebra. So imagine I want to know the x such that minus 2 divided by the absolute, what am I saying, divided by x minus 1. So this expression is equal to 7. And I ask us, well, what values of x will give this? So there are several ways to do this, but the first is, well, this is if and only if. So I could write this as the absolute value of minus 2 divided by the absolute value of x minus 1. It's my second property here. I'm assuming x is not equal to 1, otherwise I'd be dividing through by 0. So this has to be equal to 7. Okay, so now what can I do? Well, I can use my very basic rules of arithmetic. I can cross multiply by the absolute of x minus 1 and divide through by 7, and I would end up getting the absolute value of x minus 1 would be equal to, well, the absolute value of minus 2 divided by 7, I'm just trying to do one thing at a time here really, and that's equal to 2 divided by 7, isn't it? Because the absolute value of minus 2 is 2. So now what? Well, if the absolute value is equal to 2 over 7, that means the actual value must be equal to either plus or minus of that. So it's got to be either plus or minus 2 divided by 7. So we've got two options, and if you go through each of them, this is if and only if x is equal to, what are the options? I think it's 5 over 7, 1 minus 2 over 7, or let me just make a little more space. Or it would be 1 plus 2 over 7, which is going to be 9 over 7. Those are the two options. So a very standard piece of algebra there. Okay, so multiplying and divide plays very nicely with the absolute value. Unfortunately, the absolute value does not play so nicely with addition and subtraction. And this can cause some serious confusion. Okay, so if I take the absolute value of a plus b, okay, if I take the absolute value of a plus b, how do I relate this to the absolute value of a and b? Well, you see a and b, they could both be positive, and then the absolute value of a plus b would just be a plus b. So it would be equal to the absolute value of A plus the absolute value of B, but you could have nastiness with negatives. So all we can really say in this situation is this is less than or equal to the absolute value of A plus the absolute value of B. So this is always true. Now, the thing about this is it has a name, and you may have heard it before. It's called the triangle inequality. The triangle inequality. And the first time I saw this, I was like, why is that called the triangle inequality? That's madness. It doesn't make any sense at all. It's called the triangle inequality because when you think about this in 2 dimensions, if you want, and this isn't completely obvious because we've not defined a few things, but the basic idea is the following. So this is very loose. Bear with me, right? Basically, the idea is the following. If I have a triangle, and let's say I label this length the absolute value of A plus B, and this length the absolute value of A, and this length the absolute value of B, just for example. What's true of a triangle? Well, the length of one side is always less than or equal to the sum of the lengths of the other 2 sides, isn't it, right? So that's basically the reason this is true. You've got to think in 2 dimensions, and we're really only thinking in 1 dimension because we're just thinking about points in a line, but that's the reason it's called the triangle inequality. So if that helps you to remember this, very good, right? It's not obvious why this is related to a triangle just yet. It's something you'll see later on in future courses, but that's how I remember it. There's a slight variant of it as well when you have a difference. So the difference is the following. So if I have a difference, then this is greater than or equal to, well, the absolute value. The absolute value of A minus the absolute value of B. In fact, it's a bit better than that. It's also equal to the negative of that as well, so it's actually equal to the absolute value of this to really confuse us. This one is used much less often, but it always has to be like that. Okay, so that's another result which is pretty useful. Not used as much though. The main one you should look at certainly is the triangle inequality. Now, when would you use this? So this is the kind of thing that you will use quite a lot at certain points in calculus, and I want to give you kind of an example of how it might turn up. So this is going to seem a little bit, how do I put it, an arbitrary question. It'll be a bit different than others that we've seen, but it's kind of an example of how the triangle inequality shows up. So find a number, let's say capital K, so a constant, such that if the absolute value of x is, let's say, less than or equal to 2, then the following expression is less than or equal to k. Right, let's try and wrap our heads around this. So what we're really doing here is the following. We are restricting x, okay? So this statement here, where are we? This statement is the statement that x is in the closed interval minus 2 to 2, okay? Because your distance less than or equal to 2 from 0. So as x roams around in there, this expression here is going to roam around as well, isn't it, right? It could move all over the place. It could move from 1 to 50 to minus 60, anything like that. What we're trying to do is to find a number that's big enough that it'll capture it, essentially, right? So this expression can rove around. Who knows what it's going to do? But let's imagine that this expression roves around between, I don't know, let's say minus 50 and 36. So imagine as 2 moves around minus 2 to 2, this expression moves between minus 50 and 36. Well, then we could choose k to be 100, for example, because that's definitely big enough to completely capture the expression. So this is an example of trying to bound something, finding an upper bound for an expression, or maybe an absolute bound for an expression because we're taking the absolute value. So you look at that and think, well, that's some weird question. Trust me, it's a very important question, as you're going to see later on in other classes. But how do I approach it? How am I possibly going to do this? So what we need to do is to look at this expression very carefully when it comes down to it. So in this case, let's take a look. So the absolute value, so we're trying to bound this above. We want a number that's big enough to be always bigger than this if 2 is between -2 and 2. Now the thing about it that's confusing is you've got a combination of positives and negatives, don't you? You've got your kind of positive, and then a negative there. So there's going to be weird cancellation here. So what we're going to use is the absolute value, the triangle inequality, to be absolutely guaranteed of an upper bound. So the triangle inequality tells me this has to be less than or equal to, well, the absolute value of the sum of each piece inside. 2x cubed plus the absolute value of minus x, I suppose, plus the absolute value of 3. Okay, so that there is the triangle inequality. It's a little bit different because there's 3 pieces, but it's exactly the same. So let me try and write this reasonably neatly. So the triangle inequality. Okay, right. So what do I know now? Well, I can tidy this up a bit, can't I suppose. So what we conclude is the following. This expression, so this expression here is bounded above by, okay, the first piece. I can use the multiplicative properties from above to write this as the absolute value of 2, which is just 2 times the absolute value of x all to the power 3. That's the multiplicative property. Plus, well, the absolute value of x, it's the same as the absolute value of minus x, plus 3. Now, what I have at present is now a sum of just stuff that's positive, right? All I'm adding together is positive things. So if I am able to find some numbers, okay, so I'll erase this in a second, but if I find a number here, which this is smaller than, and a number here that this is smaller than, and of course a number here that this is smaller than, I would know the whole thing would need to be smaller than the sum of them, wouldn't it? So let's think, can I do that? Can I do that? So there's a restriction here that I've not talked about. The restriction is this. Well, I'm assuming the absolute value of x is less than or equal to 2. So what do I know? I know that the absolute value of x less than or equal to 2, that's going to imply the following. It'll imply that this sum what's the biggest it could be? Well, it's going to be the first piece. The largest it could be, well, the biggest it can be is if the absolute value of x is equal to 2. So this has had to be 2 times 2 cubed plus 2 plus 3. So what's that equal to? That's equal to 2 cubed. What is it equal to? 2 cubed times 2. That's 16. 16 plus 2 is 18, sorry. Plus 3, it's equal to 21. So what do I know? Let's just kind of go through this carefully. So the absolute value of x less than or equal to 2, that guarantees that the following is true. It guarantees that my original expression, this here, has to be less than or equal to, well, first of all, I know by the triangle inequality it's less than or equal to this piece. But now this piece is less than 21. So by the transitive property, I know it has to be equal to, well, strictly less than or equal to, 21. So this, at this point, I'm using the transitive property. transitive property. That's just the statement that A less than B and B less than C implies A less than C. So this is like your A, this is like your B, and this is like your C. So A is less than B by the triangle inequality. B is less than C by the restriction on X. So therefore A is less than C. So K equals 21 will do. So the conclusion is will do. There are probably better choices. Right? There's probably a smaller K that will work. But all I wanted was a single K. So this is a sophisticated example. This is difficult. This is the kind of thing you'll do at various points in your calculus classes. This kind of idea of bounding some expression above, making sure it doesn't get too big. So I thought I'd go through this just because it's a good example to see, and it's an important use of the triangle inequality. Really, it's one of the only uses of the triangle inequality that I can think of in lower division calculus classes, so it's a kind of a good place to see it. So the last thing we'll think about is roots. So roots is thankfully much easier, assuming things are defined. So if I take the absolute value of the nth root of A, well, this is equal to the nth root of the absolute value. You can bring it inside. And we are making an assumption here. We're assuming this is defined. This side is always defined because you can always take an nth root of a positive number. The other side may not be. So for example, if I was doing the square root of -1, the right-hand side would make sense, but the left-hand side wouldn't, so this would be just meaningless. So we're assuming defined, so i.e. the only restrictions would have to be A is greater than or equal to 0 if n is even. That's the only restriction. Otherwise, we're totally fine. We can take nth roots for anything else. Okay, so let's do one. So this is certainly not anywhere near as used as other things, but it's important to know it. So find x such that, this is more straightforward, find x such that the cube root of x plus 1 is equal to 4. So do I have any issues here? No, I can take the cube root of absolutely anything. Right, cube root of anything, so I've got nothing to worry about. So this is if and only if the cube root of the absolute value is equal to 4. So now this is basically an equation where I have an exponent which is constant, namely a third. So I should use my exponent laws. So what I should do is take the cube of either side. So if I take the cube of either side, that undoes the cube root, just to give me the absolute value of x plus 1. And this is equal to the cube of 4. So the cube of 4 is equal to what? Is equal to 64. Okay, so now this is if and only if what? If and only if x plus 1 is equal to either plus or minus 64. Not many options. So this is equal to x is plus or minus 64 minus 1. So it's either going to be minus 65 or 63. Good example. So just to recap, absolute value is a measure of distance from your number to 0. That's what the absolute value is. It behaves very nicely with respect to multiplication and division. It just splits apart exactly as you'd hope. It doesn't, unfortunately, for addition and subtraction. It's quite a lot more complicated. The absolute value of a sum is only less than or equal to the absolute value of the sums. Just maybe as an example, just to illustrate this. I mean, if I did the absolute value of 2 plus minus 1. Well, this is of course equal to the absolute value of 1, which is 1. But if I was to take the absolute values of each individual piece, well, that's of course equal to 3. So that's just a really solid numerical example. Okay, so they're strictly less in that case. And you have a version for the negative as well. It's just a little bit of a mess. It's not so important. And this example is tricky. So very often you use the triangle inequality to bound sums and differences of things from above in some manner. So this is something that won't turn up at the beginning of your calculus classes, but it will certainly turn up at some point. So this is a tricky example. I really recommend going through this very, very carefully at the moment, just to make sure you understand each individual step, because if you put the time in now, when you do come to it in your classes, it'll be much more understandable. And finally, roots, super nice. It's kind of exactly as you'd expect.